Hello. It has been a long time since I started working on MapDB 2, probably a couple of months, and I haven't really written anything. So I thought I will make a quick video about code changes I made in the MapDB 2. This is unscripted, and it's a very quick overview of MapDB internals. It's not supposed to be for users, more like for the developers who wants to have a look in the code changes in MapDB internals. I will make a proper documentation and more introductions a bit later, but this video should be sort of guide for people who are interested in MapDB internals. It's unscripted, unprepared, so bear with me if I'll be slow in some parts. This will be sort of code walkthrough. I just finished coding last major change, so I want to sort of give overview of the changes I made in MapDB. Today is 18th of January. I expect MapDB Alpha 1 to be released in about 2 weeks before end of the January. It should be released together with some documentation and stuff. So, but I want to make sure that people who want to go into internals have something to go by as well, and this stuff is still fresh in my mind. So the current state of MapDB, basically the major goal for MapDB 2 was to rewrite some components and to make MapDB faster. The goal was to outperform Java util collections and RocksDB. It's sort of valid goal, and it's still on track, but and I have some very small benchmarks which kind of looks very promising. I haven't written benchmarks yet. I just finished the coding, and it's not even fully optimized code yet, so there is still some potential and stuff. So I will address the benchmarks and stuff a bit later. Also, some API like DBmaker is not fully functional if it doesn't fully respond to the changes and configuration options which are in the code. So let's start. So basically the current state is that I finished modifying the collections. I revamped the engine infrastructure. I rewrite the storage format and stuff. What is missing right now or not missing, but it's a code from the old MapDB 1, which will probably be redesigned to sort of improve our snapshots, concurrent transactions, and right now the asynchronous writes are not completely implemented or not implemented at all. So let's get started with the code. So one of the major changes in the MapDB 2 was MapDB B3map architecture and B3map B3map key serializers. In the MapDB 1, we had a huge problem with deserialization overhead, because if let's say you have a root, you have a nodes, you have a B3 nodes, you have a root, then you have a N1, N2, or the directory level 1, the directory level 2, the directory level 3, and then you have a final leaf nodes. Okay. The problem with MapDB was that for each lookup, for each map get, the B3 map had to deserialize all the nodes on all the way to the leaf, and basically if you take that each dir node had like 32 keys, and you will have like, I don't know, five levels, it gives about 150 keys to be deserialized just to perform MapDB get. And obviously this is horrible for the read amplification. Basically, rather than scaling up with and the interval will be like something, should be for b3 something like logarithmus n. If you count right amplification, you get something like logarithmus multiplied by m, where the m is some sort of really high number related to the deserialization overhead. So basically the problem with this is that the B3 performance wasn't that great as soon as the node started reaching, as soon as the B3 started reaching sort of huge sizes. And in MapDB 1 I haven't thought this will be sort of problem, because I thought that deserialization overheads is nothing I can do about, and it turned out I actually can do loads of about it by using primitive arrays and be sort of CPU cache friendly and stuff like that. So what happened in MapDB 2 is that I moved loads of logic into B3 serializer, B3 key serializer, and I took advantage that if you have an array of keys, basically each leaf node, or each node, for example leaf node, is composed of array. Let's say you have a leaf node, you have a map with long, where the long is key and the strings are values. So in that case each leaf node will be composed of array of longs. I will use scala notation, and then you have values which are some sort of strings. The thing is, in here I can take advantages of merging long array into a single collection, and it can be primitive collection. And this obviously saves loads of space, and because each object in Java is like one pointer, then a header, object header, class reference, and so on. So basically in the first case, in the long array of long object, I will have maybe 16 or even 25, 26 bytes per entry, per key. And in the second case, I can just have a 8 bytes. And because leaf node, because direct B3 operations, or the most common operation on the directory nodes, on the B3 nodes, is binary search. Obviously binary search is much more faster on the array of primitive longs, because they fit all in the CPU cache and so on. So the major change in the MapDB 2 for the B3 is that it uses primitive or specialized collections for the deserialization, for the representation of the objects. This sorts the read amplification problem a lot. It improves it a lot. Then there is second stuff which I will talk about, which is sort of called partial deserialization, but I will probably talk about it in some later videos. It should solve it completely. But the key in here is that this actually, with this setting, the B3 map can now outperform Java util hash map in most settings and in most configurations. And it can outperform it even with the small size sets, when the garbage collection is not really kicking in. Obviously if you have a 100 million items, the Java util hash map is not just, it just doesn't work anymore, because the garbage collection is too small, is too big. So, but the nice thing about is that the B3 map can outperform Java util hash map even with 1 million collection, where the garbage collection is not really issue yet. So there is B3 key serializer became a sort of go-to object which handles anything related to the B3 keys. The node itself is not really, where is the node, B node? I need their node, yes. Okay, B node here. As you can see, the B3 map on its own is not really aware of what type of the object is the keys. It just has generic reference to the object, and for any sort of function, for example, size of the keys or number of keys, where is it? B3 nether node. Yeah, for example, putting new key and stuff like that, it has the reference key serializer or corresponding method in key serializer. For example, in here, we are in the B3 map, but the B3 map on its own has just the keys in here are just generic object. It doesn't have any type. So in order for the B3 map to find what is the actually size of the node, it has to call key serializer, which will actually decode the value from the keys. And the way how it works, for example, in here, in this example, I will take the longs, which are probably easiest to understand. So in here we have a longs. So longs are in here are represented as a primitive array of longs instead of object like this, and all the operations like such as deserialization and serialization is performed in the B3 key serializer, which is handling the longs. But then you also have a comparison methods, comparison methods, which are obviously much faster because you don't have to cast the data, you don't have to unbox the primitive long. Then you have a comparator, you have empty keys, even the length, because B3 map on its own cannot decode the type of the object and cannot decode the length or number of keys in the node. But you also have operations such as put keys, copy part of the keys, and array collections, and even delete key from the array of keys. And what is most important is the find children. This is binary search performed on the node, on the array of keys. And the amazing here is that, or very good here is that it's everything is primitive values. So this can be optimized very, very well, and it's good chance it will fit in the CPU cache. Another very nice thing in here. So I think I went through the longs. I will go also through the strings, because I think that's another nice thing in here. The string array can be, if you have a array of strings, okay, if you have an array of strings, you can represent it this way. One of the improvements could be representing it using array of characters. And another improvement, if you are using ASCII, 7-bit ASCII or 8-bit ASCII only, you could use it. You could represent it as arrays of arrays. Yes, that's it. Okay. So both these optimizations are available in MapDB, but we go much farther. The string serializer represents, the string key serializer represents array of keys, array of strings as basically as one huge byte array or char array, and then there is separate array of offsets. So this will be value, and this will be data. So let's say you have 32 strings in here. All those data will be packed into single byte array. So this will be like 32 multiplied by length of all the keys. and then you will have 31 integers, which are starting offsets of each key. And the nice thing about this is that even though the character arrays or array of array is still very nice, it's not very CPU friendly, and binary search and stuff like that will be problematic because you have to jump a lot in the memory. If you have everything on the single byte array or in the single character array, everything can nicely fit in the memory, and the binary searches in here are very fast. Outside of this, MapDB actually can the B3 string serializer have much more optimizations. For example, it can detect if all the strings in the key array are 8-bit ASCII, and in that case it will use byte array, and if they are Unicode it will use character array, and it can switch between those two dynamically, sort of. So basically it will save loads of memory and stuff like that. Then there is usual stuff like common prefix compression, but similar stuff was in MapDB 1. So for example, if you have two strings, AAABB, AAACC, and so on, only it will be serialized as AAA, and then you will get the only differences. So obviously this is much less data than repeating AA 3 times and so on. So anyway, that's usual optimization in MapDB, but the key change in the MapDB 2 is the primitive keys, which brings a much better performance because the unboxing and binary searches and stuff like that are much more CPU cache friendly. So the performance bonuses are huge. I think I'm talking like 30, maybe 50%. I haven't fully investigated the benchmarks yet. I am not even done fully with the optimizations, or in some ways I didn't even started optimizing the code yet. This is just architectural optimizations, but I already have a benchmarks when the B3 map outperforms Java util hash maps for the small sets. So I think that's very nice. I'm quite happy about this sort of result. So just the second major change in MapDB is the change in the serializer, in the serialization. MapDB has a bunch of serializers. Basically, serializer is object which turns the okay, I will just have a look at the definition here. Yeah, that's the definition of the properties, inheritance. Yeah, sorry for this. MapDB has a bunch of serializers which are specialized. So for example, you have one serializer for character, one serializer for string, booleans, boolean array, blah blah blah, and so on. And then there is a default serializer which handles everything, which is sort of generic. It can handle anything you throw at it. In MapDB 1, this serializer was sort of not very CPU friendly, or not very performant friendly. It was very fast in some ways, but one of the this is oh wait, I need to switch the branches here. Okay, that's the serializer base from the MapDB 1, and what I wanted to show here was this if else clause. Okay, so basically MapDB handles like MapDB serializer base in MapDB, which is generic serializer. has a special cases for most common data types. So there is special case for the integer. So you basically get like common numbers which are serialized some way. Then you have a minimal value, maximal value, and then you have a sort of interval which you can fit into single bytes, 2 bytes, and so on. Basically, it's a loads of code, loads of jumping and loads of conditions and stuff. And it cannot be really optimized in the small methods to be just-in-time compiler friendly. I think just-in-time compiler compiles only methods up to 300 bytes or something like that. So this code will run in the interpreted mode, and it wasn't really great. Plus, you will, if you are serializing something, you have to you have to go through all those if else. Basically, it wasn't that great performance-wise. So in MapDB 2, I changed it using lookup table. Basically, there is map of class. Oh, wait, I'll be there. Yeah, deserialize. We are here. Read unsigned. Oh, it's a serialization code. Sorry. So, yeah. There is still some common stuff which will be eventually eliminated. But what is important here is this lookup map. Okay, this replaces all those if-else conditions, and basically this serializer map is identity hash map where the class is key, and the serializer is the value. So rather than going through all those if-else conditions, we just have take the class of the object and have a lookup in the lookup map, take a serializer and just serialize that thing with generic stuff. Obviously, this piece of code is much smaller than all those if-else conditions. There was like 60 of them. So I expect the serializer base in MapDB to be much faster than in MapDB 1. MapDB 2 should have this class much faster. There are more optimizations in the serializer base, such as it's more configurable. So, for example, it's not in the code base, but if you have a B3 map, key serializer or value serializer, it will not have to implement serializable. Anyway, there is more changes coming, or some of them are, but this is sort of big architecture change in MapDB 2. This sort of stuff I want to address in this video. So basically, we introduced the lookup tables for the most common. Yeah, I think that's one of the things here. We introduced the lookup tables for the most common data types, and we eliminated this huge if-else code block. Okay, so another change is in the hash map, or H3 map. H3 map is the data structure which provides hash map and hash set. Basically, I'm not sure if you know how hash map works, but there is this sort of hash table, which is basically set of which is basically a long array of numbers. And in MapDB we are using sort of foldable tree, but anyway, what is important here is that there was tree structure, and each node was array of longs, and there were 3 levels of this, and the length of each of those was 128 multiplied by 8, okay, which is about 1 kilobyte if I'm correct. So basically this is obviously huge amount of memory for one kilobyte per node. It has to be deserialized, serialized. So in order to kind of not all of those values are used. Basically the hash map only use some small partition of this hash table, because some values are not present and stuff like that. It's a bit complicated. So anyway, so in order to compress the values in hash map 2, in hash map 1, I was using array of arrays, and the size of the primary array was 8, and the sizes of secondary array was 7. All this again multiplied by 8. The problem here is that again each long array is the object on its own. It's not really CPU cache friendly and so on and stuff like that, blah blah blah. And because it's a record ID, but record ID is not really 8, not 8-bit bytes, but only 6 bytes. So I was looking at the ways to improve this sort of memory consumption of this thing, and I came up with the data structure, which is sort of much more CPU cache friendly, and it's using only single byte array, and it's not always, and it has much better memory consumption. The first 16, yeah, there is 128 bytes or 128 values. So first 16 bytes is the bitmap. Oh, sorry, this was replaced with this, and in this structure the first 16 bytes bitmap, okay, and if the bit is present, the value at this offset is present. If not, it's not present, and then basically our data, which is series of 6-byte record IDs. I haven't. The thing is about the thing about this is, again, it's very similar to optimization as in B3 map. Key serializer, it's very CPU cache friendly. It's using less memory, and it's very fast to create byte array without manipulating garbage collection and new object and so on. So I haven't evaluated the performance yet of the hash map, but I expect to be about 30, maybe twice faster compared to old version. The related code is in the keys, in the serializer again, somewhere here. Yeah, this is bucket serializer, or oh my god, I'm a little bit slow these days, but bear with me. Anyway, this is not important. It's there if you want to have a look. I'm sure you can find it. It's a directory serializer or hash serializer or something like that. Yep. So since we are talking about the serializers, I will go in the serializer. Yeah, another one more important thing. The hash map had a, if you wanted to use hash map with primitive byte arrays or long arrays or integer arrays, those things do not implement equals and hash code, okay. But one of the changes in MapDB 2 is that the serializer class is aware of the data structure or data. It basically, the serializer is now responsible for anything which is related to interpreting the data, so it can actually compare the data. So B3 map doesn't need and it also B3 map doesn't need the comparator, providing you specify the key serializers such as if you basically specify, yeah, anyway, it can compare the data, but it also implements the hash code and the equality. So now if you want to use primitive byte arrays in the HT map or B3 map, all you have to do is to specify the proper key serializer, and the map will take the equality method and comparison method and hash code methods directly from the serializer, because the serializer now actually provides hash code methods. It's yeah, it's over here. So the default implementation is just using Java object hash code, but obviously it's overridden in some other serializers. It also provides equality, and I think I'm going to implement comparison very soon. It's not here yet, but it's trivial change, so it should be in alpha 1. Where were we? Yeah, the nodes. So basically in the MapDB 1 for the hash map you need the hasher, and for the B3 map you needed comparator. I'm not really sure what was the code in here, probably something like that. Okay, well, I'm not sure if it's MapDB 1 compatible, but basically all this is gone. You don't have to use it. As soon as you specify the key serializer, a map is aware of the comparators and stuff like that. So that's a nice thing, I think. Yeah, that's there are a number of changes in the tree map or B3 map, which I'm not going to really go through. It will be on a separate video. There is key or some sort of per node aggregation and stuff. It's a bit complicated, and I'm not really sure how it will work yet fully, or I have some prototypes, but I will leave it out of this video. So let's go to the engine wrapper hierarchy and the concurrency and stuff like that. It's one of the nightmares in MapDB 1. Okay, I will go in this code, and this is important here. This value 128 is number of log on each layer in MapDB 1, and the implication of this is that if you have 5 layers, you end up with almost 600 logs, and it's obviously going to be slow. And all those logs have to be logged in the commit and stuff. I got some criticism, and it's something that I'm not really proud, and this was fixed in MapDB 2. So let me explain how it works in MapDB 2, how concurrency works in MapDB in general. MapDB uses engine. Engine is basically map where the record ID, which is long, is assigned to some sort of data. Okay, and it's a little bit more complicated, but I think you will get the idea. And in order to support concurrency on this thing, there are 16 or 120. We use similar method as segmented concurrent hash map in Java utils in Java 6 and 7. So basically we take number of logs, or basically we take 16. Let's say that we have a concurrency factor 16. In here it's 128, but so we will get 16 maps and 16 logs. Okay, and number of entries in here is concurrency factor or concurrency scale. Okay, so and if you want to put or modify one of the collections, you basically use some sort of hash or low level hash on the key. So in order to put something in the map, what you will basically do is calculate the log position, which is usually calculated by some sort of modulo or modulo reminder. Okay, then you take a log, then you take a map, you do operation on the map. You have to keep you have to remember that each of those maps is not thread saved. Okay, the thread safety is provided by this segmented log, and so on. So basically this is pretty much standard technique. I call it segmented locking, but I think you get the idea. The problem in here is that MapDB has an engine hierarchy. It's something I was very proud of sort of design, because it was very object oriented and stuff like that. The way it works, you have an engine, which is basically the map of where the number is the key and the byte array is the data, whatever. And then you have various implementations. So one of them is storage, or store in the MapDB terms, and then you have various wrappers, and those wrappers provide functionality such as caching, asynchronous write, and there's even transaction and so on. Okay, so if you want to provide some sort of functionality, you will end up with something I called engine hierarchy. So on top of you will have, for example, asynchronous writes. Then you will have a cache, instance cache. Then you will have a store, and I think we could provide the transaction on top of this, or let's keep it simple. So basically we have 3 layers in here. Okay, the problem is each of those layers is thread safe. So the store has its own set of log, then the cache has its own set of log, but it's also using concurrent hash map, so another set of log. Okay, and asynchronous writes have its own set of logs, and so on. And there is loads of write log and blah 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 blah. So if you have a concurrency factor of 128, this is 128 logs, this is 128 log, this is 128 log, and this is 128 log plus another 50 logs. And all of this masquerade has to be sort of synchronized. And if you have a shared state, which is like rollback and commit, you basically have to log all those 500 logs. So this is sort of performance nightmare if you are aware of CPU cache, which I wasn't aware of in MapDB 1. So in MapDB 2, this is all gone. The exception hierarchy is still in the code. I will probably eliminate it completely in a couple of weeks. The cache hierarchy is gone, and the way it works is now store has its own set of logs. The number of logs is reduced from 128 to 16, which is another change I will go through a bit later in this video. And then you have a cache inside the store. Okay, and the asynchronous writes are also inside the store, and I will probably provide write cache and so on, all inside the store. Okay, and the beauty about this is that the cache, the asynchronous writes and write cache, and all those classes, they don't have to be thread safe. They don't need they can be thread unsafe, because they are already protected by locking mechanism, by segment locking in the store itself. So I only need a single set of locks, and obviously in this case the number of locks is reduced from 600 to 16. And this is a huge deal, because for example the commit and rollback required locking all those 16 locks, all those 600 locks in MapDB1. This was totally revamped in MapDB 2, but I think you get the idea. Okay, so I think this is the first part of this video, and I will pause now and I will continue in the second video.